Hello. As mentioned earlier in my previous video on the electromagnetic induction, the first installment, I had mentioned that we'll be discussing about the motional EMF in a conductor. Now, the conductor that produces the EMF while moving in a magnetic field causing a change in its flux, the motional EMF is thus produced. And we will be obtaining the relation or the expression for the motional EMF. It's obviously related to the case of changing flux and thus the EMF that we had obtained from Faraday's law, but the expression will be a bit different because it involves the motion as well as the velocity term will come into picture, and so will the length of the considered conductor. Now we'll be using three methods to obtain the same expression because we'll be dealing with different cases. Obviously the conditions will be the same, but we can consider three cases for them. We'll see how. The first that we'll employ is the expression that we'll be obtaining for the motional EMF is by considering the Faraday's law or taking the Faraday's law into account. So using the Faraday's law, what we see is that in the given figure, we have an arrangement where we have a cylindrical conductor and we are seeing that we're getting the top view of it. So we are only considering the flat surface of the cylinder at the top. It continues downward into the paper or into the screen that you see. And it's placed between the north and the south pole of the magnets, which produces a uniform field from the north pole towards the south pole. And as you can see, the motion of the conductor is towards the right of your screen with a velocity v. So the straight conductor, now let the length of the conductor that we have considered, the length of the conductor is L. It's taken to be L. You cannot see it obviously because it's into that plane that we have considered over there. But however, we can make a assumption over there. So now it supposedly moves across a distance dx. So it moves through dx, that is, it cuts through a distance dx along the direction of motion in time dt. And as a result of that, we have the velocity, which is a constant one, that is equal to dx over dt. Now, the magnetic flux that will be produced, that will be d phi in the given time dt, and that will be equal to the magnetic field multiplied to the area. Now the area of the cylinder that is exposed as it cuts through the magnetic field in time dt will be simply equal to, now this is the field. If we consider the sideway view of it, this is the field. Now the field is supposedly acting into the plane, and we have the conductor over here, and it's a cylindrical wire, supposedly a conducting wire, and now it's moving along this direction, and in the time dt it has swept through a portion dx. Now the length of the conductor as we know it is equal to L, and we are seeing the top view that is from over here, and it has swept through a distance dx in that time. So the area that is exposed is this area that I have shaded. Now the area over there is going to be the length multiplied to the distance that it has passed through in that time dt. So the area is a dA, and dA is equal to L multiplied with dx. So d phi will be B dot with dA, and as you know that the area vector will be aligned with the magnetic field, so we have this B dot product with dA to be simply B dA. That will be a cosine of 0, so that goes to 1, and then we have this value to be equal to B dx times of L, or BL dx. Let me write that as BL dx for convenience. Let's just take the dx in brackets, so we have L over here. Doesn't really matter. Now with this, the rate of change of flux will obviously be giving me the Faraday's law. As per the Faraday's law, it will be giving me the induced EMF, and because this is going to be a single turn or a single coil form instead of n number of coils, so this is simply d phi b uh, d phi b divided by dt, phi b or phi whatever we have considered. So this is equal to b, the L comes back to its place, and dx over dt, and dx over dt as we know is v, so this is BLV. Now this will be the magnitude. As per the Faraday's law, we can give the magnitude over here. The direction obviously will be something different as compared to the not as compared, but as per the Lenz's law. So as per Lenz's law, the direction will be in a way to oppose the cause that is producing it. So any guesses for that? You can predict the direction by using the Lenz's law. While you make the guess, what we can also consider is that in case the object or the conductor is moving in some other direction with respect to the given field. So the field is moving, as you can see, from the top to the bottom in that figure above, and if this conductor is supposedly moving along this direction, making a certain angle theta with respect to this is angle theta with respect to the field, then we'll have the cosine component, or the sine component of it to be acting along that line. So this is a case where we can consider the sine component, and as a result of that, instead of V, we'll be ending up with E is equal to BLV sine theta. So that's a special case in case the conductor is moving in some other direction with respect to the given field instead of moving at right angles to it. So this is one case. As I mentioned, we will be discussing three cases. This was by using the Faraday's law of electromagnetic induction directly. The next case that we'll be considering is the law of conservation of energy. Now, as we know that energy can neither be created nor be destroyed, changes from one form to another, what we have at hand is that if we consider this diagram, then as I mentioned, that you can predict the direction of the induced EMF as well as the induced current by means of Lenz's law. It tells that it opposes the cause producing it. Now, with the magnetic field in that given figure, in that second figure that we have drawn, the magnetic field going into the plane, and what should be the direction of current so that this mechanical force that is being applied to move it is opposed. That means the opposition must come in this direction, that is on to the left of your screen. So in order that happens, because we know that the force acting on a conductor of a certain length due to a magnetic field will be IL cross B. So the current which flows through the conductor, and that the direction of the current is the direction of the length considered. So L cross B must be towards the left hand side, and in order that happens, in order that we get the L cross B to be acting towards the left with B into the plane, the current must flow in the upward direction, that is along this line over here. The red arrow that has been marked. So the current moves in the upward direction, and we consider the direction of the length in along that line, and from L cross B, the cross product gives us the force to be acting in the opposite sense, so that the net force that acts becomes zero because there is no acceleration involved. The force is constant in order to move the object towards the right hand side, the force that we employ. And that's a constant force. Obviously the velocity that was taken, that was constant, so the acceleration in that case is zero, and the force is the net force is going to be zero. And because the net force is going to be zero, what we are going to follow is that the the forces are eventually cancelling out each other. That means we have the F, which is the force that is employed, minus the force that is provided by the magnetic field on the conductor, which is ILB. Now the cross product is obviously going to end up with a 90 degrees directions. It involves 90 degrees directions because the current moves in the upward direction while the field goes into the plane. So obviously they are at right angles. So ILB sine 90, and sine 90 goes to 1, and this net force that we are going to get, that will be 0. And as a result of that, what we are going to get is F will be simply equal to ILB in terms of the magnitude. Now the rate of the work done is obviously the rate of work done, that is the power that has been employed, is equal to force multiplied with the velocity. And if we are multiplying the force with the velocity on the left hand side, we must multiply this ILB factor by V as well. And with that available to us, now this rate of work done, that is the power that is available, that power that has been employed as per the conservation of energy, that has to be equal to the EMF induced multiplied to the current, which is the power that has been generated. So this power that has been employed in the circuit, in the production of EMF, has to be completely converted to the electrical power that is generated in the circuit due to the induced EMF. And as a result of that, we compare these two factors, that is the expression for the induced EMF and the power that is obtained, and by comparing them we obviously cancel out the I terms, and finally we are left with the expression for the induced EMF, and to rearrange them we obtain E is equal to BLV, which is the expression that we had obtained right in the previous case here as well. So this expression is for motional EMF, this expression is for motional EMF. The same thing obtained in a different manner and using a different principle. The above principle that we used, or the above case that we used, was the Faraday's law of electromagnetic induction, where we consider the rate of change of flux, that is d phi over dt. And in the next case we are considering the conservation of energy, where the power employed to move the conductor through the field is completely converted into the electrical power that is generated across the circuit. So now we move over to the third case, where we use the concept of the Lorentz force. So in this case what we are going to consider is the Lorentz force, where if I were to draw the conductor again with the field involved, the second diagram that we have considered. So this is the conductor, so it's slanting over here. That's more or less the case. And then we have considered the field lines to be acting into the plane. Finally, we have the magnet. Now if this conductor is moving along this line, along this direction, that is with the velocity v, now any charged particle over here, let that be equal to let that be having a charge q. Now that charged particle over there is going to be moving with a velocity v as well towards the right hand side, at least for now. And the magnetic field, now this is a positively charged particle that we have considered, and the magnetic field that is acting into the plane in that figure that we have. So q v cross b, there will be a force due to the magnetic field which will be acting on that charge in motion along with the motion of the conductor. And as a result of that, if we apply the cross product of v cross b, so v going to the right and b into the plane, so we curl our fingers and we get the force due to the magnetic field on that charge, positive charge that has been considered, that is plus q, that takes the charge or drives the charge to the upward direction along this line. So that's the direction and that's the force due to the magnetic field which is acting on it. Now this charge gets accumulated, so all the positive charges will be accumulated on that top, and the negative charges conversely will be accumulated at the bottom of the conductor, as we see. And this accumulation continues, this motion continues as long as we do not have an electric field which is pushing the positive charge downward with force, because it will be repelling the positive charge with the electric field now developed from the top towards the bottom because of the difference in the potential. So there will be an electric field which will be because of the potential difference that has been created with the accumulation of the positive charge at the top and the negative charge at the bottom. And this electric field would be driving the positive charge in the downward direction, repelling it, and that results in the force due to the electric field. So now this force due to the electric field is balancing the force due to the magnetic field, and then the positive charge or even the electrons in that case, they tend to stop. And when that is achieved, we achieve a steady state in that case, and the forces, thus we have this Fe to be equal to Fb. Thus we have the Lorentz condition over here with the directions oppositely acting, because Fe plus Fb will result in 0 with the net motion of the charge completely vanishing. So we end up with Fe minus Fb to be 0, and finally we have Fe is equal to Fb. Now this will result in the charge multiplied to the electric field for the electrostatic force, and we have the magnetic force to be equal to the q v cross b, and again, as we know, v and b being perpendicular to one another, the cross product will result in sine 90, which goes to 1. The q's can cancel out because we know that the electric field is simply the potential over the length that has been considered, the potential difference. Here the potential difference is the EMF, we represent it by that kind of E that I have just written, and that divided by L leaves VB on the right hand side. So finally we have the expression for the electric for the EMF that has been induced to be equal to BLV once again, and this is the expression same as we had obtained in the previous cases, but we have employed a different rule over here. So you can employ different concepts and different rules which will obviously result in the same thing, because it is dealing with the same thing. So this is more or less the expressions involving the motional EMF. In the next videos we'll be discussing about the eddy currents, followed by the self mutual inductions, and many more to come. Till then, thank you for watching.